Alrighty guys, we are looking at the day 2 IM1 Functions notes. We're going to continue talking about linear functions. So our warm up here, we have the sequence -2, 2, 6, and 10. So what we've got here is our first term, our second term, our third term, and our fourth term. If we wanted to, we could work backwards, just get in that habit of determining that 0th term. The 0th term would do the opposite of adding 4, which is our common difference. We would subtract 4 to go in the opposite direction. So our 0th term would be -6. All right, so let's look at what it wants. What is the formula for this arithmetic sequence? Graph it on Desmos and attach the image below. So if we're going to come up with a formula for this thing, let's just go with what we know. We know that a sub n is equal to a sub 1 plus the difference to the times n minus 1 if this thing is arithmetic, which we have determined, where a sub 1 is our first term, -2, plus the difference of 4 times n minus 1. So that right there, that is our explicit arithmetic formula, okay? Explicit arithmetic formula. Now, for number 2 says consider the equation y equals 4x minus 6. Well, if we use the equation y equals 4x minus 6 and we evaluate at each of these points 0, 1, 2, and 3, what that would look like is this. Well, we're going to go y is equal to 4 multiplied by, let's throw 0 in for x first, I'm talking about this 0 right here, and minus 6. And what would y equal? You just go through and you solve. 4 times 0 is 0, so we have 0 minus 6. So y is equal to -6. So when x is 0, y is -6. But hold on, we've seen this already. When x was 0 up here, or our term number was 0, y was -6. Just an observation. Let's try another one. Let's try y is equal to, and we'll go 4 times 1 minus 6. It's going to be the second one in our table here, right here. Okay. Now what that gives us is 4 times 1 is 4, and 4 minus 6 gives us -2. So it doesn't look like this is a coincidence. It looks like this might be happening for a reason. Now, if you continued and did the same thing for 2 and 3, you would get 2 and you would get 6 here. Now, what you need to realize is that this is the same thing as what's happening up here. So this formula right here needs to be derived from this guy somehow, some way, because what this explicit arithmetic is giving us, we're also getting with this formula. So the goal today is to make the connection between this explicit arithmetic and that guy right there. You may recognize it as slope-intercept. Take a look through those learning goals. And hey, look, there it is, slope, initial value, y-intercept. So slope-intercept must be on tap here. So let's look at example number 1. Example number 1 asks you to describe the domain of the sequence. Now, if you go back to your day 1 notes, we talked about domain a little bit. The domain are your x values as they exist in this sequence. And the x values here appear to be 1, 2, 3, and 4. Okay, so the domain of our sequence are 1, 2, 3, and 4. Now, identify the common difference. Easy enough. We can just look at, okay, what are we adding to get from one term to the next here? 2, 6, 10, 14. So it appears that our common difference is equal to 4. We're just adding 4 each time. And C asks us to draw a line to model the linear relationship seen on the graph. Okay, well, if we draw a line to model this, let's see what tool I can use here. Is there a straight line tool? Yes. Okay, so from here straight on through, and mine's just a little bit off. Let me see if I can line this up a little bit better. If we line this thing up, oh shoot, I thought I could move it. Darn it, mine's just a little bit off. Okay, but you can imagine it going through those points. So if we want to come up with an equation for this line, I want you to consider, let's see, when we're making connections here between arithmetic and slope-intercept, what we see here is we have this common difference occurring, okay, where we're adding 4. Now, where do you see that in the slope-intercept form? It appears to be the slope. So this maybe just kind of be an observation or a guess at this point, but the common difference appears to be the same as the slope, okay? A very important observation there that we were making in class. Now, this guy right here, the -6, okay, so this -6 right here, this -6 appears to be, and let me get the pen, sorry about that. This -6 appears to be the 0th term. Okay, so this right here, the negative 6, this appears to be the 0th term, but it's also known as the y-intercept if we're talking about slope-intercept form. So if we're going to try to write an equation from this guy, it would help to have our 0th term, potentially, right? So it appears that we're adding 4 each time, so our common difference is plus 4 each time. Okay, and we could work backwards here to get this 0th term by subtracting 4 to go backwards, right? If we're adding 4 each time. So if we subtract 4 here, our y-intercept would be negative 2. Our 0th term would be negative 2. Now check it out. Our line here appears to go through at negative 2 at our y-intercepts. Okay, so if we attempt to write an equation here, and I think that we can all do that in explicit arithmetic, so we want to kind of get you guys in the direction here of using slope-intercept, and even better, let's do slope-intercept form in function notation. F of x is equal to our slope, which is our common difference of 4x plus our 0th term, and our 0th term was negative 2. So we just do minus 2. Now you can check that in Desmos, but I would bet you that that is going to be the same line as what we're seeing here in this graph. Okay, now example 2. I want you to take a close look here. We have this explicit arithmetic formula of a sub n is equal to 2 plus 4 times the quantity of n minus 1. Now, what this worked example here is doing for us is they are showing how we can convert the explicit arithmetic into slope-intercept form here. And we have slope-intercept form of 4n minus 2. Now, the process, pretty simple. You just distribute the 4, okay? You just distribute the 4, so you have 2 plus 4n minus 4. Basically, they just reordered their terms here and then combined like terms, and they have 4n minus 2. So basically what we have here is this explicit arithmetic is the same as slope-intercept form. So compare the equation you wrote to the arithmetic sequence to the explicit formula written in function notation. What do you notice? Once again, the common difference is the slope. The 0th term is the y-intercept, okay? So if you compare the common difference with the slope, what do you notice? They are the same thing. They are the same thing. Now our boy Hank here, he's talking about the y-intercept of a linear function, and he's saying that it's the same as the first term. Now think about this. This doesn't quite make sense. Come on, Hank. So actually, what he should say is the y-intercept of a linear function is not the same as the first term. It is actually hold on. The y-intercept of a linear function is the same as the first term of an arithmetic sequence. I would say that it's the same as the 0th term of an arithmetic sequence. Okay, so the y-intercept is not actually the first term, it's the 0th term. Okay, now I would read through this. Basically what it's talking about is first differences. And what we determined in class here is that if a sequence has a common difference, then it is linear. And I should be more specific here. If a sequence has a first common difference, then the sequence is linear. And that distinction is going to be important when you get to IM2 next year, because you're actually going to see what's called a second common difference. So let's look at this first one here. Looks like we're adding 4, adding 4, adding 4. Because we're adding 4 each time, this right here is linear. Okay, and in this second one, it looks like, once again, we're adding 4, adding 4, adding 4 each time. It's actually the same sequence as the one on the left, except it starts with the 0th term. So this too is linear. So if we jump down here, take a look at these. This one appears to add 3, and then add 6, and then add 9. So what's curious about this is actually the second difference is common. Now that doesn't count as linear, because for it to be linear, the first difference must be common. And this one, the second difference is common. That's an IM2 thing. Hold off on that. Let's look at this one. So right here, we're going to say not linear because it doesn't have a first common difference, okay? So let's look at B. So that's for A. Let's look at B. It looks like B is, how do you get from one term to the next? It looks like we subtracted 4. Looks like we subtracted 4 again. Subtracted 4 again. This right here is a first common difference. Therefore, this is a linear sequence. it has a first common difference. Now, if you check this next one, same thing's happening here as A, kind of. Okay, so it looks like we're adding 3, adding 5, adding 7. That is not a first common difference. Once again, that is actually a second difference. Again, you're going to have to wait until IM2 to kind of dig more into that. But for now, you can at least determine, for the same reason here, this right here is not linear because it does not have a first common difference. Okay, the same thing as what we were just talking about in A. Okay, so the only one that's linear here is B. And again, why? Because it has a first common difference. All right, guys, give the self-assessment a try. Feel free to watch Khan explain this. Probably a lot better than me. He's amazing. If you haven't checked out Khan in math yet, do so. Otherwise, give that self-assessment a try. Watch the video, make your corrections. Give that portfolio a try. Good job.